welcome to the next lecture in this video lecture series. In this lecture, we'll be talking about inter-process communication. Processes are of two types. They are either independent, where a process doesn't need the help of any other process for its execution. And the second category is where processes can be cooperating. That is, one process, it takes help of some other process to complete its task. So the question that comes up is, why do processes need to communicate? Processes need to communicate because majority of the times you need to share some information among these processes. But why? When do processes share information? There are many situations where processes need to share information. Majority of the times is when you want to have parallelism which needs to be exploited. That is, you have a certain task, you would like that task to be divided among a number of processes, and these processes would be working in parallel on those sub-problems. In such cases, processes often would be communicating among themselves. So it's some kind of modularity and convenience that you want to bring in solving problems, and that requires splitting up of jobs and allocating them to independent processes. But because these sub-problems would require will have some kind of dependence, that is, they would need some information from some other process, they would need to have some kind of mechanism to communicate. So these are the reasons why processes have to communicate among themselves, which means there must be some way, some mechanism by which a process would be able to transfer some data to some other process or receive some data from some other process. Okay? An operating system is the one that provides these mechanisms to the processes. So OS provides different mechanisms for inter-process communication. And in this lecture, we are going to talk about those mechanisms provided by the operating system. So let's look at the different mechanisms which the OS provides. The first one is something called the shared memory. Okay. We so far have discussed about the memory occupied by a process. Okay. But now we are going to talk about how, by utilizing a shared memory segment, one process would be able to communicate with another process. Okay. Then we would talk about something called signals. That's another mechanism through which one process would be able to transfer some information to some other process. Let's say some process would like another process to be stopped, okay, or killed. So what is the mechanism through which that can be done? And the technique that we are going to talk about is called signal. Then we have another very interesting concept called pipes. That's a data structure maintained by the kernel through which two processes would be able to communicate. One process would be writing onto this data structure, the other would be reading from that, and by this they would be able to communicate. We will see the working of this pipe. So let me write it here because they belong to, okay, and then we have one more mechanism of communication which we call the message passing. Okay. So that is, one process would be communicating with another process by sending and receiving messages. And in relation to that, we will be talking about inter-process communication mechanism called sockets. So these are the 5 different IPC techniques that the OS provides to processes for inter-process communication. Now interestingly, out of these 5, some processes, some techniques, say 1, 2 and 3, they are used for communication among processes that happen on the same machine. Okay. So that means if you are talking about a same machine and you have a process P1 that would like to communicate with a process P2, it may take help of the kernel and it can utilize this kernel to communicate with P2. So that means P1 and P2 can communicate among themselves by taking help of the kernel. And if this is what happens, that is both P1 and P2 lie on the same machine, okay, that is on the same host, you will see that these are the three techniques that we will be using. Okay, so this is what happens in case you would like IPC. So either you will use shared memory, or you will be using signals, or we will be using pipes. On the other side, when you have processes that are residing on, say this is some P1 and this is the kernel of a particular machine. So this is, say, host 1, and now the two processes that would be communicating, they reside on two different machines. In that case, so this is, say, host 2. In that case, if these two processes would be communicating, it will be like this, that P1 will make use of kernel 1, kernel 1 will be communicating to kernel 2, and then it would reach P2. So this is the path of the communication that happens between P1 and P2. So in this case, you have the two processes residing on two different machines, and if this is what happens, then we use either a message passing concept or we'll be using sockets. So these are the IPC mechanisms that we'll be talking about next. Talk about the shared memory IPC mechanism. As already discussed, this is an IPC technique which is used for communication among processes which reside on the same machine. So as the name implies, in this particular case, processes which would like to communicate would share a certain memory segment, and someone will be writing something into that, the other will be reading from it. And this is how they would be communicating among themselves. So let's talk about what is a shared memory. So we already have known so far that processes occupy a certain range of addresses in the memory, and that's called its address space. So every process has or occupies a certain space in the memory. So let's say this is the physical memory, and this is certain process P1 that occupies certain space in this. So this is the address space of P1. Though I have written this P1 to be the address space of P1 to be a contiguous range of addresses, it may not be so. We will see that later on while talking about the memory management. But this may be distributed. So whatever it is, let's assume for the time being that P1 occupies certain space in the primary memory, and similarly there is one more process P2 which also occupies a certain address space in the memory. Now these two address spaces are independent. Even if P2 has been formed from P1, so let's say if P1 had fork resulting in a process called P2, even if P2 was created from P1, we have seen that earlier, still the newly created process or the child process will have its own space in the memory. So the address space of the child will be different from that of the process, right? And that makes these two processes independent. Okay. So that means these two processes, they do not have any portion of the memory which is shared. Now let's say if these two processes like some memory segment to be shared, so what is the process to do that? So in order to have a shared memory between P1 and P2, either of them must request the operating system to provide such a shared segment. That means the operating system keeps track of a number of such kind of shared segments. In order to make use of one of them, one of the process which would like to communicate has to request for such a segment. So one of the process would request for such a shared segment, and the OS would provide this P1 with a shared memory segment. So let's say this is the shared memory segment that has been created. Now if these two processes would like to communicate, the mechanism is that P1 would be writing something into this shared memory and P2 would be reading it from this. Okay, or the other way around. P2 would be writing something into the shared memory and P1 will be reading it from there. So this is how the two processes would be communicating among themselves. Now interestingly, this shared memory which was maintained by the operating system now is part of the user space. So let's say if this is the portion which is the OS, the shared memory was currently held by the operating system. One of the processes, P1, had requested the operating system to provide such a shared memory. The OS provided that, and now this shared memory segment is part of the user space. So if this is the user space, so the shared memory now is part of the user space, so that both these processes P1 and P2 can make use of this shared memory as a regular memory segment. Okay, what do you mean by that? Let's see. So P1 we saw that this is the physical memory, right? But we have already seen that a process has another view of its address space, and that is its virtual view, the one that is actually seen by the CPU or the program. So let's say this is the virtual address of P1 and this is the virtual address of P2. So the concept that the concept behind the allocation of this is that when the process requests this operating system to provide such an shared memory segment, right? OS, it provides a certain range of address which is either predefined or the amount of memory a particular process, say in this case P1, is requesting to be treated as a shared memory. So the size of that particular shared memory also has to be asked by P1. Okay, so P1 puts a request. So it's a request for the shared memory. The OS provides that shared memory, it grants that shared memory request and provides a certain range of addresses to be treated as a shared memory. And what happens is, you already have known or seen that if you look at the virtual address of P1, it consists of the code segment, the data segment, the stack and the heap. Okay? So the shared memory that is created will now be part of, so this shared memory will now be part of the data segment of the process that requested for it. Okay? So the request, OS grants this request and this shared memory that is being provided gets attached. So this is the shared memory that gets attached to the data segment of this process. Now all processes that would make use of this particular shared memory segment should also attach this segment to itself. Let's say in this case P2. If P2 is going to make use of this shared memory segment, it also has to attach that. So once this shared memory gets attached to the data segment part of the process P1 or process P2, so that's nothing but an extended data segment now. You can treat this shared memory segment as an extended data segment of both process P1 and process P2. But since these range of addresses are shared, which means anything that this process writes onto that is made available to P2 as well. So this is the mechanism of shared memory, the shared memory usage to bring about inter-process communication. Okay. So now how does OS provide or carries out these request, attach, etc.? Oh, once the job of the shared memory is over, okay. So let's say some shared memory was attached to process P1 and P2, and after the memory, the segment got attached, P1 would write something into that, and P2 would be reading. So let's say this is what goes on. Okay. So once this reading writing process of the execution regarding or utilizing this shared memory is over, the next thing to do is whatever shared memory has been attached to this data segment should now be detached. So that has to be removed from the data segment of both process P1 and P2 so that OS can reclaim that. So there are three operations primarily which are executed in order to work with a shared memory. Number one, a request to the OS to provide the shared memory. Okay. Number two, the attachment of the shared memory segment to the process. And number three, detachment of the shared memory once you are done. So these are the three operations that need to be worked with in order to work with the shared memory segment. We have seen how while working with shared memory, we come across three different operations. The first is the request to the OS to provide the shared memory. Second is to attach that shared memory segment to the address space of the process. And third is detaching that process once we are done with done with the shared memory. Now let's see the different system calls provided by Linux in order to perform those three operations. The first, as you remember, was the request to the OS. So the process, okay, so the process P1, it puts a request. Let's say this is the process P1. So the process P1 puts a request to the OS. Okay. So this request is put through a system call called shared memory gate. So this is the system call that creates a shared memory segment. Okay. The SHM gate creates the shared memory segment. So it's a request put, and what it returns the ID of the segment. So the segment that has been provided by the operating system to the process P1, its ID is returned. So this is of a data type integer, so that's the ID of the segment that is returned to the process P1. Okay, and what does SHM gate take as the arguments? First, there's a unique identifier associated with every such shared memory segment. Okay, let's take up this simple example here. So let's say we are using SHM get. The first parameter is a key, which is a unique identifier of the shared memory segment. So usually you declare the value of key, maybe say something like 9126, and that is what you pass on to this first argument. So this is the unique identifier that you attach to the shared memory segment, which will be created once the OS allocates that. Then second is the size. The size of the shared memory that you would like to create. In this case, in this example, we create an array of 2 integers. That's the amount of size that we would like to be treated as a shared memory. And finally, we have flags. So this is the typical example of a flag for this SHM get system call. This is a way in which you would like that particular shared memory to be treated with. So a flag called IPC underscore create, which likes to find out whether a shared memory is already in existence or not. If it is not, then it has to be created. So in case a shared memory with a key 9126 has not yet been created. So this flag would ensure that a shared memory will be created, a certain ID will be associated with that as provided by the OS, a key will be attached to that particular segment, and this is the permission that that particular segment would have, the different user permissions, right? The read, write, and the executable permissions. So this is typically the usage of the shared memory gate system call. Okay, so once the shared memory gate is there, so we've already seen that now that the data segment of this process P1 would now have this shared memory attached to that. Okay, and this will now will have the key 91626, and what it returns to process P1 is the ID. So in this we store this in a variable called SHM ID, let's say. Okay, so that's the usage of shared memory gate. Next, once this shared memory has been provided or it has been created, the next thing that needs to be done is it has to be attached to the existing address space of the process P1, as we see here. So it's not only process P1, all processes which would like that particular process, the shared memory segment with this identifier or key to be, or with this key and this identifier to be attached to its address space should call that. Okay, and the way to do it is through this system call called SHMAT. So what it does is it attaches the shared memory segment to the address space of the calling process. So whoever makes use of this, that shared memory segment gets attached. Okay, so it could be P1, it could be P2. So P2 could also like to attach, in that case it also to make use of this SHMAT system call. So what are the parameters of this? So what you need to pass to SHMAT is the ID of the shared memory that has been created, which was obtained by using SHM gate. Then a pointer to the shared memory address space. So a pointer to that should be passed so that both the processes would be able to know that this is the address range from where it will be attached to my address space. So you need a pointer for that, and obviously some flags, that is how we will be working with that particular address space. So this is the typical usage of SHMAT. And finally, when you are done working with the shared memory segment, you need to detach it from the address spaces of both processes. And in that case, the only thing that needs to be passed is the shared memory ID, and we will be making use of the system called SHMDT, which detaches the shared memory from both the processes. So these are the three system calls that we use in Linux in order to work with shared memory. Now let's see a code to see the working of this three shared memory, these three system calls. This is a typical example of how we make use of the three system calls in order to work with the shared memory. So in this code, a process forks another process, and the parent and the child, they make use of a shared memory where the parent writes something into the shared memory and the child reads it from there. We normally know that whenever a process forks another process, the child process and the parent process, they have their individual memory images. So the address space of both the parent and the child are separate. As a result, if a process makes some changes in its own address space, it does not reflect to the child. The child is not able to see that. So in order to have something done by the process which would be seen by the child, we make use of the shared memory segment in this case. So it's something like this, that the process P, it would first request the OS to create a shared memory. The shared memory will be provided by the OS. Then the process, once the request has been done, so the parent, okay, the shared memory would be attached to the parent. the shared memory has been created. So the parent process has requested the OS to create, the shared memory has been created but not yet attached, and then the parent forks. So we have the parent and the child, okay, and now each one of these will be attaching this shared memory to its address space, right? So the child will also attach it to the address space, so that whenever the parent will be writing something to this, and the child will be reading it from here. Okay? The child will be reading it. So this is the way in which this code works, and in order to because the parent process has created the shared memory, or the shared memory has been created, and then it forks. So the key associated with that particular shared memory, the key associated with this shared memory, okay, would automatically pass on to the child, because the child is created after the shared memory has been created. And in order to do that, we make use of this key called IPC private. So it's a private key which is associated with the shared memory which is being created, and that is passed on to the child once the parent forks it. Okay, so let's go to that. So we make use of SHM gate, SHM AT, SHM DT, and then we have something called shared memory clear. We'll talk about that later on. All these system calls will be made available through these two libraries, the IPC.h and the shared memory.h. Okay. Right. So we declare two pointers, A and B. We'll make use of that in order to trace the shared memory segment in the child process or in the parent process. So let us assume that we are in the main process, and the process now wants to request for a shared memory. So it makes use of the SHM gate, and already discussed that in this case we are going to use a private key, because that would automatically be passed on to the child which will be created. So I'll make use of IPC underscore private. We'll make use of a shared memory which is an array of 2 bytes of 2 integers, and then we'll make use of the IPC create flag in order to create the segment in case it has not been created, and we check whether the permissions have been provided to that segment. So the value that is being returned by SHM gate is the ID of the segment, the shared memory segment that is created. Okay. That is held in the integer called SHM ID, and now the parent forks. Okay. So it creates the shared memory, and now it forks to create a child process. Right. So if we fork and the return value of the fork happens to be 0, which means we are in the child process. Recall the return value, the process management APIs that we had discussed. Fork returns a value 0 to the child process and the ID of the child process to the parent. So in case the return value happens to be 0, we know that we would be executing the code for the child process. So this is the code for the child process, where we would be first attaching that created shared memory segment to the address space of the child process. That is done through SHM80, and what it returns is a character pointer. Okay. So in order to convert it into an integer, we typecast it, because B is a pointer to a type integer, so we typecast it to it, and we store it in B. So B now is pointing to the corresponding segment that has been attached to the child process. Okay. Now we'll be running a loop. That's what we are going to do in the child process if we are going to work with the memory that has been attached. So what we are going to do is, the child will be reading the values pointed to by B. So it will be reading the values B0 and B1. So here we have the shared memory, which is nothing but two segments. So the one that gets attached to the child, so the one that gets, so the shared, let's look at the view here. So this is the child and this is the parent. So we have a data segment of the child here, and that's the shared memory segment that has been attached. The parent data segment, that's the shared memory segment has been attached. Okay, now the pointer to this in case of child is B, so the pointer to that is B. So this is of 2 bytes. So when you are at the child process, the pointer to this shared memory is through the pointer called B. So this is B0 and B1. So what the child will be doing is, it will be running a loop and will be checking, or will be reading the values of these two, B0 and B1. Okay. That's what we are expected to do in the child process. And once you are done, you will be detaching this. So you will be detaching this part from the child, and that is done by using the system called SHMDT. You pass the value of B to that, and it detaches the segment that has been attached. Okay. Now, what if we are in the parent process? The parent is the writer process that writes into that shared memory segment. And what it does is pretty similar to that. We make use of the shared memory attached system call. We pass on the shared memory ID, and we don't have any flags. So let's keep this 0, 0. So what it returns is again a character pointer which is typecasted to an int and is stored in A. So A now points to the shared memory segment attached to parent. So that's A. Okay. So now we initialize the two values A0 and A1 respectively by 0 and 1. And as I told you that the parent is the writer process. So it writes, and what it writes is it updates A0 by the initialized values of A0 and A1. That's what A0 is updated with, and A1 is updated with the updated value of A0 and A1. So you have two new values of A0 and A1 after within the loop. So that's what you go on doing. So you the previous two values of A0 and A1 is that's what you keep on updating in every iteration of this loop. And the new values that the A0 and A1 are updated with, that's what the writer writes into the shared memory. So it's like this, that at every loop, the parent writes something to the two values, and the child in turn, it reads it from there. So once done, and oh, by the way, once the writer writes it, we have introduced the wait system call, which remember was a system call to make the parent wait until the child is over. So the idea is that parent writes something into the shared memory and waits for the child. The child in turn, when scheduled, would read those two values from the shared memory, and once done, it's the same. We detach the shared memory segment from the parent process, and finally we'll clear once the reading and the writing process is over. And for that, we make use of another system call called SHMCTL. So that's clear the shared memory that has been allocated to the process. So mere detachment does not remove or does not, it simply detaches it from the address space of a process. But if you would like that shared memory to be provided back to the OS, you need to clear it, and that is the reason why we use SHMCTL. So this is a typical example of how we make use of these three system calls in order to work with the shared memory. The mechanism in Unix that we are going to talk about is called signals. So it's a lightweight IPC mechanism for processes and the kernel. So processes, they communicate among themselves or with the kernel. And what are signals? Signals are software interrupts which are sent to a program to indicate that an important event has occurred. So it's an interrupt that is sent to a program, and that triggers that particular program and makes the program aware that there is some event which has occurred and you have to do some task or some action that needs to be taken. These actions, some of them are default, so accordingly, depending on what kind of interrupt has been sent, these default actions have to be taken, or they are told that this is what you need to do. So some will be default actions, some will be told. But whatever it is, so they are some kind of software interrupt, which is an indication that some event has occurred. And that event can be anything. It can range from a user request, or it can be some illegal memory access. So any kind of events that can be. It can be an illegal memory access, so which means that the program would now be told that, okay, you are not supposed to access this part of the memory, and automatically an exception will be created. Or there will be some user request, some user has triggered some kind of interrupt to be told to that particular program. So it can be anything, whatever it is. So through this signal, the program is made known, that the program knows that there is some event. So here we have some signals that are typically used. We have provided 3 signal names. Each signal has a number associated with which the signal is identified, and these are the description of the corresponding signals. Primary among them are SIG init, which has signal number 2, and that's a user generated event. Okay, so if the user wants to send some interrupt, he simply presses the interrupt key, control plus C, which instructs that particular program to be interrupted. Okay, so that's a user generated interrupt. The other one could be the signal hang up, which is to stop the current process. Okay, we'll talk about that in just a moment. So these are the typical signals, and these are some of the, as you see, so each signal has its corresponding default action. So in order to check what are the signals that your system supports, this will display the signals supported by the system. So in case of a Unispace system, you can simply type in kill -L to show the signals and the corresponding details. Okay, now as we told that these are interrupts that are sent to the program. So every interrupt, as you have already known, that has some default action. Something is done in case an interrupt occurs. So the default actions that are associated with the signals can be, some of the signals may cause termination. Okay, so you terminate a process. You already have seen that. Okay, in case of, let's say, this is the signal. So you would like that particular process to be stopped or terminated. Okay, same thing is in this case of, say, kill. This would be a forced kill. You would like that to quit immediately. So it can either terminate some process, or it can be ignore a signal completely, or it can be something as core dump. Dump is this particular event. In case a signal which leads to core dump, it creates a file called core, and which holds the memory image of the process at the time when the signal was generated. So you would like that process or memory image of that particular process to be stored in some file. So in case a signal creates a core dump, so the file called core, which holds the memory image of the process when that particular signal was triggered. Then we can stop a process. or we can continue a stop process. So all these can be done through signals. Okay. Now how do you send signals? So the way to send signals is, number one, as you've already seen, it can be user generated. To simply press the interrupt key, Control C, and what it does is it sends a signal to that particular process. So in that case, a Control C would send the sig init signal, which in this case is signal number 2, and which would make the program realize that the user has sent an interrupt and the normal flow of execution of the process should stop and we should do something else. So in that case, it's like to terminate the current process. Okay. So that's one way of sending a signal. The other way is through something called a kill command. So let's say there's a process and the process would like to terminate some other process. So let's say the bash wants to terminate some other process. It's very often you come across this situation. A particular process is malfunctioning or it is taking too much of memory and you would like that particular process to be terminated. In that case, you would make use of this kill command, which would generate this sig kill or sig hub, either of the two, depending on what you pass as a parameter. So the syntax is kill followed by the signal that you would like to pass and followed by the process ID that you would like to terminate. Okay, so in case you would like a particular process to be terminated, you first need to find out its process ID, which is available through different commands. We've already discussed that. Either make use of the top or the PS command. Know that particular process ID that you would like to, the ID of the process that you would like to terminate. And then you pass either the signal number 1, which will hang up that particular process, or if you would like that process to be killed immediately, okay, you make use of either this. So you can have either -1 then followed by the PID, say, or you can make use of the -9 to send the sig kill command. So this is a typical way in which one process sends a signal to another process. In that case, if this is running in the bash, so it means the bash is sending a signal to process number 1926 and makes it stop. So that's how we make use of signals in order to have an inter-process communication. The next IPC mechanism that we are going to talk about is pipes. Okay. So consider a situation where a process would like to write a set of values and the other process would like to read those set of values. So a typical system construct to perform this kind of IPC is a pipe. So it can be treated as something of a shared buffer. So we have a process P1 which would like to write something, and there is a process P2 which would be reading from that, and the kernel maintains some kind of a buffer. So the process 1 writes into that and the other reads it from here. Okay. So this is a shared buffer, we can call it as a pipe. And in the case, as in the case of any buffer, so if this process wants to read from the pipe but finds that there is nothing written in this pipe, then it has to wait. Similarly, if the pipe is full, that is this buffer is full, then and this process wants to write something into that, then it has to wait. So this two processes have to maintain that depending on whether the pipe is empty or full. So you can treat pipe as this kind of a buffer that is maintained by the system, and the processes make use of this buffer in order to communicate among themselves. Okay, but this communication is a half duplex communication, that is a one-way communication. One would be able to write into that and the other would be able to read from that. And how is this reading and writing process, how does this happen? So system treats this pipe as a file. So the pipe is nothing but a file that the system maintains. And we've already seen while maybe in our programming classes that when a system deals with a file, there are a lot of operations that are done on files, and those operations are like read, okay, write. So in order to perform a read or a write operation on a file, the file first needs to be opened. So typical usage is to make use of this library called fopen. We typically use that in C. So what does an fopen, what is it used for? It's used to open a file, right? So what is the meaning of this fopen? What does an fopen return? So what fopen returns is a file descriptor. So what is that? Now the kernel, it maintains information about each running process, and whenever a process opens a file, it makes or it keeps track of what are the files that have been opened by that particular process, and that's the system table. So the system table maintained by the operating system keeps track of all the processes and all the files that each process has opened. So whenever a new file is opened by a process by making use of this system call, okay, then a new entry is created in the system table, and the index of that corresponding entry in this system table is what is returned as the file descriptor. So whenever a file is created, let's say a file by the name F1 is created, its entry is created in the file descriptor table or the system table maintained by the OS, and the index of that is returned as the file descriptor. And as we know that, hence all operations related to the file, whether it is fread or fwrite, needs this file descriptor. Okay, needs this file descriptor, and that is exactly how pipes are also dealt with by the system. So that means, similar to files, whenever a pipe is created, okay, because the system treats pipes as files, you need to have a file descriptor associated with that. But unlike files, in a pipe we would like to read and write at the same time, and that is why we need two file descriptors. One for the writing purpose, so there must be a file descriptor associated with that for the write purpose, and the other one should be for the read purpose. So if a process wants to write something into this particular pipe, it has to make use of the write file descriptor to perform a write operation on that particular pipe. And if this process wants to read something from this pipe, it has to make use of the read file descriptor, only then it can read from that. And that is the reason why we say that pipes are half duplicate communication, one-way communication between two file descriptors, because pipes are treated by the system as a file with two file descriptors. So the moment a pipe gets created, there are two file descriptors which get associated with that, one for writing purpose, other for reading purpose. A typical example of a pipe would be, as a very common command that we type in our Unix shell. So this is a program called ls, this is the pipe, and this is another program, the word count program, -n. So you can treat this as a program whose standard output is fed as an input to this program. So both program or both processes are running concurrently. Okay? So it's not that one stops and the other, both are running concurrently, except that the std out of this is provided as std in for the next process. Okay. Now, this is a typical example of a pipe where you see that this is the pipe that joins these two processes, which enables the communication between these two processes. Now, pipes are of two types. They are either named pipes or unnamed pipes. This is a typical example of an unnamed pipe, and the one that we are going to show here is also an unnamed pipe. Why we say unnamed? Unnamed because these pipes are created, used and destroyed within the life of a set process, within the life of a set of process. So they exist as long as the process is there, and then the moment the process is terminated, these pipes are removed. They don't have a name. Okay. The other kind of processes are called named pipes. They are nothing but FIFOs. Okay. And they have a name associated with that. So what we normally do is, these kind of processes, they extend beyond the scope of a process. So their endpoints, so if these are FIFOs whose endpoints are accessed, can be accessed outside a process. So that's the named processes. So we will be restricting our discussion to unnamed process because they are the most common ones that we come across. So how do we create an unnamed process? So to create an unnamed process, we make use of the pipe system. So we make use of the pipe system. And what do we pass to this pipe system call? We pass the file descriptor. And as I've already told that this particular pipe, which is treated as a file, has two file descriptors. So that means you need to have a file descriptor which is, let's say, a typical array of 2 elements, and that is what we pass as the input to this file descriptor, to this pipe system. So this eventually creates something of this kind. So it creates a pipe which is a file maintained by the system, and one file descriptor is for the writing purpose. So if we call this as write, FD1 is for the write and FD0 will be for read. Now let's see how in a single process we can make use of these two. So say suppose we have declared a file descriptor, an array of 2 elements, and we have passed that as this. So the typical user process will have, so this is the kernel and the pipe is here. So this will be the write file descriptor. So it's FD1, and this is the read file descriptor, which is FD0, and this is the pipe which is maintained by the. Now let's try to see how we can introduce, the same pipe concept, but in say 2 processes, and that too if they happen to be happen to have a parent-child relation. So in case you have a parent and a child relation among 2 processes, so the idea is that you open a pipe, okay, then you fork another process, and then you would close the appropriate ends. Let's see what we mean by this. So the idea is that you have a parent. Okay. So the parent, it creates a pipe. Right. So that is, it makes use of this pipe system call, passes this file descriptor. So it makes use of this. So it creates a pipe in the kernel, and it also creates the file descriptors read and the write. So you have your FD1 and you have your FD0, and now you fork. Okay. So the moment you fork, you create a child process which is the replica of the parent, and that means a pipe is maintained by the child also. So the two file descriptors which were opened for the parent process have also been opened for the child process. So now you have the child process which also has a write file descriptor, okay, and a read file descriptor. So this is the situation that we have. Okay. So that means after you fork, this is what the situation is. But do we need all that? Do we need all these 4 file descriptors? No. If you would like the communication to happen between parent and child, where the parent will be writing and the child will be reading, then we don't need this. In that case, because parent would only be writing, there is no need for the parent to read. And similarly, the child would only be reading. It has no need to write. So in that case, we can simply remove these 2 ends. Okay, and that's what we call. And how do we do that? Okay, so we use the close system call and we pass. So for the child, so if you are the parent, right? If you are the parent process, then we would remove the FD0. So we would be closing the FD0, and if you are the child process, then you would be closing the FD1. That is your write. So that's what you do. I assume that there was a byte that has been done here. Because it's a child, the same thing is available there. So this is what we do. Close the appropriate end. So that's what we do. And that leads to this unidirectional communication between the parent and the child. Now, in case you would like to have a bidirectional communication, so in that case, you may make use of 2 pipes and then connect them accordingly, so that you can come up with a bidirectional communication. So something like this. So you can have, say, a parent process, and this is the kernel, and here you may use 2 pipes, because now we need to have bidirectional communication. So we ensured that writing by the parent and reading by the child. So we know how to do that. Reading by we just saw how we can make use of this. Okay. So this is write of FD1. Okay. So maybe so you can have your write FD1 of this and FD0 of this. So in case you would like to have the other way around, you can simply repeat the process, but in that case you have to make use of another pipe, pipe 2, and this time it would be the other way around. So this would be the FD1 for pipe 2, and this would be the FD0 for pipe 2 for the parent. So this would ensure that you will have a bidirectional communication. Okay, so that is about the pipes. This is one more IPC mechanism that's very commonly used, not only for processes that run on the same machine, but also applicable for processes that run on 2 different hosts or 2 different machines. So what is this? It's called message passing. So the idea is that processes, they would communicate through exchange of messages. So one process, it creates a message queue, and another process, it sends a message to this queue, or it sends a message to this queue via OS. So it's something like this, that you have two processes, and the two processes, they, so here we have, let's say, process P1, and what the process P, this is the kernel you have. So one process would create a message queue. So this is nothing but a linked list of messages that are maintained in the kernel, and you have the messages which are maintained as a queue. So this is the one that has created this, and there's one more process, P2, that would like to retrieve or send a message. Okay, so in that case, this process would be able to perform some operation on that message queue. It is either going to read or send a message. So in order to do all that, this typical message passing technique which is provided by the OS, the OS provides a number of system calls such as these in order to send and receive messages from this message queue. So the processes that would like to make use of this message queue would be using these system calls to send and receive from them. So this is how by maintaining a message queue, one process communicates to the other. So it's not about writing something into a shared memory or into a shared buffer such as pipe. Rather, it's a queue which is maintained by the kernel, and one process writes something into that, and the other process reads from that particular queue. Now, as you can see, this is the message passing shown for two processes that are running on the same machine. But interestingly, this message passing concept can be extended for processes which are running on different machines. So it's really something like this, where you can have a process which would be making use of its kernel to send a message. This would in turn send it to a kernel maintained or running on some other machine, and this message would be carried from this kernel K1 to kernel K2, and which in turn would be passed on to another process P2. So it can extend the boundaries of two processes running on two different machines.